Hi, today we will learn self-inductance. Self-inductance is electromagnetic property of an inductor, due to which it opposes any change of current flowing through it, that is inductor. Like how in mechanics, mass opposes any change of state of rest or state of motion. So mass is called measure of inertia in mechanics. Now this inductance, self-inductance opposes any change of current through inductor. So self-inductance is called electromagnetic inertia of any matter. It is inertia. Here you can see the diagram of a resistor, a zigzag formation. This is the symbol of resistor. Now this second diagram, this is in the shape of helix. This is the symbol. So let us see with the help of a diagram that how magnetic flux is related to current flowing through this circuit. When current is zero, there is no magnetic flux or field lines. Current is increased. Here in ammeter you can see current is increased, so magnetic field lines also has increased proportionally. If you further increase current in ammeter, you can see field lines has strengthened and there is a change in magnetic field lines, magnetic flux. So an EMF will be generated that will oppose this change in magnetic flux, this increase in magnetic flux. So EMF will be induced in such a way, in such a direction that it will diminish the increasing magnetic flux. Here this B is magnetic field due to induced EMF due to back EMF as it is opposing the increasing magnetic flux. So this is called back EMF. This will be in a direction just opposite to increasing magnetic field or flux. So a current which was previously in this direction, now a new current just opposite to that is called back EMF, back current. This will oppose this current while there is change in current only. When once current reaches to its highest value, maximum value, and then it stabilizes, then this back EMF also is vanished. So here you will see increase in current, increase in magnetic flux. And this is the maximum value of current and you have maximum value of magnetic flux. Now no change in current, no change in magnetic flux. So let us find the self-inductance of a solenoid. Here I have one solenoid with its length small l. Number of turns, as you can see, is capital N. Number of turns per unit length, that is small n, is given by capital N by small l. Now radius of the cross-sectional area is R. So this flux phi, flux for one turn will be proportional to current flowing through the solenoid. Now the same flux is associated with all the turns. So a quantity called flux linkage which is equal to total flux through single turn, through one turn multiplied by all the turns, this is your total flux called flux linkage. This must be also proportional to the current flowing through the solenoid. Now N phi will become equal to Li. Here the constant of proportionality is L, and this is your self-inductance. Or this is also called coefficient of self-induction. This self-inductance has unit Henry. Its SI unit of self-inductance is Henry. So let me find the dimension of self-inductance. You will put the dimension of flux, that is your BDS, dimension of BDS, and you will put the dimension of I to find dimension of L. Now one more thing is there, that induced EMF, back EMF, which will oppose any change in magnetic flux, will be equal to minus d phi upon dt as per Faraday's and Lenz's law. So from equation 1, this must be equal to minus L di upon dt. From here also you can find the dimension of self-inductance. So the dimension of self-inductance is equal to dimension of E into dimension of time upon dimension of current. This E is equal to your work done per unit charge, ml to t power minus 2. This is dimension of work per unit charge, means IT. For IT you will write ampere into time. So this is the dimension of EMF induced, which is equal to work done per unit charge. I have written here. For dimension of time you will be writing T, and for I you will be writing ampere. So the dimension of self-inductance comes equal to ml2 t power minus 2 ampere power minus 2. This is the dimension of self-inductance. So let us find self-inductance of a solenoid. Okay. So N phi is equal to Li. Now N is equal to your N into L, number of turns per unit length into L, and flux phi is equal to B dot ds. This will be equal to by putting the value of magnetic field of a solenoid, which is equal to mu naught N into I, current flowing through the solenoid. Here small n is number of turns per unit length, and ds area is equal to pi r square. So from 1 and 2 you can write flux linkage, and phi is equal to your mu naught Ni pi r square into N, that is your NL. So let us put all these values in equation 1. Okay, change this as 2 and this is at equation 3 because I have already used equation 1. So in 1 you will find that mu naught N square L pi r square I is equal to Li. Here I is cancelled and self-inductance comes equal to mu naught pi r square N square L. So everything I have written, N square here, L is also pi r square. Okay, so this is your self-inductance of a solenoid. You can find that self-inductance only depends on the dimensions like radius of the solenoid, number of turns and length. Here self-inductance depends on dimensions like radius, length and number of turns. And also it is depending on the nature of material kept inside the solenoid. If you take a material inside the solenoid of permeability mu, if permeability is equal to mu, then your this equation of self-inductance becomes L is equal to mu pi r square N square L. Okay, and you know that permeability of any medium is equal to permeability of free space into relative permeability of the material. Therefore, L can be also written as mu naught mu r pi r square N square L. So this is your self-inductance of a solenoid. In the same way, you can write self-inductance of a coil of N turns. You know that magnetic field B of a coil, B is equal to mu naught upon 4 pi 2 pi I upon radius of the coil. So this is your magnetic field of a coil of single turn. Therefore, B of a coil of N turns will be just N times more. So the B will become mu naught Ni upon 2R. So this is magnetic field of a coil of N turns. Now you can find inductance, self-inductance of the circular coil in this way. You know that N phi is equal to Li. So now let us put the value of all things immediately without any description. Here N is equal to NL, flux phi is equal to your B dot ds is equal to Li. Therefore, NL here B I have obtained mu naught number of turns is equal to NL I upon 2R is equal to Li. Cancel I from the two sides and you will find that L comes equal to half mu naught N square L square upon R. So this is your self-inductance in a circular coil of N turns. So by the same method you can find self-inductance of so many other current carrying shapes. Now what is self-inductance? Some work is needed to be done against this induced EMF, back EMF, so that current can be established in the coil. Now potential is equal to work done per unit charge. It implies that work done is equal to QE here. E is equal to potential. That is your back EMF. Okay, so when you differentiate the equation, you will get that rate of change of work done is equal to dq upon dt into E, IE. So dW comes equal to IE dt. Now let me put the value of this EMF induced. This is equal to your minus L di upon dt. Here you have dt. Cancelling dt from the two sides, you will find that dW is equal to minus L I di. This is the small work done in establishing small current I. So for total work done, we need to integrate equation A from 0 to I current. It implies that your dW work done is equal to, let us take the constant outside of equation, from 0 to I di. Therefore your complete work done is equal to minus L I square upon 2. So work done is equal to minus half Li square. This inductance opposed the increase of current or decrease of current. It is just opposing any change in current. As in mechanics, your mass opposes any change in state of rest or state of motion. In mechanics, you know that work done or kinetic energy is equal to half mv square. You have some analogy. If you compare the two equations, you will find that the equations are similar. What in electromagnetic in analog L is doing, the same work is done by mass in a mechanical analog of that. Mass is opposing any change of state of rest or uniform motion, and here L is opposing a change in either increase or decrease of current. So L, inductance, is measure of inertia, is inertia. In electromagnetic analog,